Hello everyone, my name is Nick Koya, and this is my amplifier. It unfortunately suffers from the condition of being incredibly cheap, and so today I'm going to see if I can improve it. So before we can fix this wonderful amplifier, we need to figure out what's wrong with it. And so I have a little test setup here where I have my scope probe on our left channel here. I have a 1 volt, 1 kilohertz sine wave going into the left channel because I just happen to put it into the left channel. And right now the amplifier is turned off, and we can see there's a little bit of noise on the screen there. Hope you can see in there. But generally we have a flat line. You know, the Fourier on the bottom here is showing nothing particularly interesting. But I got the volume turned all the way down. Let's turn the amp on, and we can see we have a little bit of a problem here. So what we have here is a 120 hertz ripple here, and the volume's already all the way down. And I can turn the volume up here a little bit, and you can see everything goes away. And this is very unfortunate because this is loud enough to hear when the amplifier is not playing anything. It is independent of the volume. I can't really show you that because I don't have it set up to subtract the input signal here, but if there's, actually I can turn off the input signal by unplugging it. So if I unplug the input signal, I can turn the volume up, you see nothing changes here. So this noise is coming from somewhere after the preamp, which is good because that means I don't have to mess with the preamp, I guess. But yeah, if we plug the signal back in here, we can turn this way down again. You can demonstrate that it does actually work, so you can bring this up by a long ways. I'm trying to cook my resistors here, but you can see that even when we're pushing some signal through here, we still have these peaks down here around 120 and a couple of harmonics. So I can actually crank it up all the way and show you how it breaks down as well. Turn this way down, 10 volts per division. So if we come up here, we can see we're doing all right. Just have the peak at 1 kilohertz, but then, right around here, you can actually see that, I mean, number one, it distorts on the bottom. Go one higher here. Clips on the bottom, but we also have that ripple on the top again. And so what that's telling me, I'll turn this down before I cook my resistor. What that's telling me is that we have ripple on the power supply. And you know, that's not very good. We don't want ripple on the power supply. We want nice clean power. So let's pop this open and see what's causing that. Alright, we got the case off the top of the amplifier here, and we can see that this is a basic chip amp. We have a, a TDA 2009, which is a 10 watt per channel amplifier, so you can tell that the labeling on here is complete bullshit. But, you know, it's an amplifier chip, so it does what it does. We have a transformer up here giving us 18.5 RMS out of here. And that goes directly into the board here, and into this rectifier, and then into this filter capacitor, and then into all of the rest of the circuitry. Now, on the one hand, that's a perfectly reasonable low-end power supply solution. The chip amp has a power supply rejection ratio that theoretically means that it shouldn't leak the ripple off of the power supply into the audio output, but we can tell that that's bullshit. It's obviously leaking into the output because we measured it. So obviously what they should have done here is they should have had a regulator on here to clip off the top of the incoming rectified waveform, and then that would have made it much easier to filter the remaining ripple out of that, and then you'd have a nice clean 27 volts DC going into our amplifier chip here. But they didn't do that, and so that means that there is a bunch of ripple in here, and if I hook up my probes and point you at the screen, we can see what that looks like. Alright, so we have the amp powered back on, and I'm just clipped to the heatsink here for my ground. And I will probe on this wire, which I happen to know is V+. And we're AC coupled here, and this is about 200 millivolts per division, and you can see that we have a lovely triangle wave there, which is not a smooth and flat DC input. And obviously we have just gobs of harmonics all over the place, starting at 120 Hertz because this is a full wave rectifier. But this is essentially what we can expect out of an unregulated power supply. You know, the sine wave will come up, it will raise the charge on the capacitor, drop off again, capacitor discharges, the next half of the sine wave comes up, and you know, you're always going to be fighting that when you don't have a regulator. If we had a regulator in here, we could crop the top off of all of those lumps and we wouldn't have that issue. Now unfortunately, the way this board is designed, you can't really just put a regulator in between the rectifier and the filter here. You know, obviously they've never put pads in there for putting that kind of part in. So we have to do something else, and that something else is going to be feeding this circuit with DC. So I have here a 27 volt, 85 watt Meanwell switching power supply. Takes AC in this side, you know, rectifies it, smooths it, runs it through, let's see, right, this MOSFET here to switch it, goes through the tiny transformer, gets regulated, filtered, and spat out here. So, it also has a little adjustment and a little fan connector if you want to put a fan on here, but we aren't going to need that. So I am going to basically mount this roughly like that. Once we get this transformer out of the way. I'm going to turn that off before I shock myself. Once I get this transformer out of the way, now I will go a little deeper dive into the circuit, because if you think we're feeding AC into this circuit, and so it's going through a full wave rectifier to feed all of the stuff off the 27 volt rail in here. You know, what could be the problem of sticking DC in here? It'll just go through the full wave rectifier and do everything as normal. But as we'll see in a moment, there's a little bit of tricky circuitry in here that we need to pay attention to make sure that we get things hooked up the right way around. So I'm going to pull this board out so I can show you the bottom side and a few of the traces, and I'll be right back. Alright, we've extracted the main board here. It's upside down at the moment. You can see that here is our chip amp. We have our, get my hand out of the way. We can see here is our chip amp. We have our rectifier back here, our main filter capacitor right there. And here is our AC input. And I'm going to flip this over. It's a single-sided board, so it's really easy to trace, and we can see that screwdriver point. We can see that our AC input comes to the center pins of our rectifier, but there is one other component hooked up right here. And that, if I can get this around here, is this diode. Now this diode actually feeds into this set of components right here, and what this is going to do is this is actually a power detection circuit essentially. So if you've ever used like maybe a very old or very low quality radio, like a really cheap clock radio or something, often what you'll find is you'll power on the radio and you'll hear a bunch of buzzing and static, and then you'll hear the music or the audio coming out. You turn off the radio, the volume drops, then you get some buzzing, and then it goes quiet once the power goes away. This here is a relay that is in the, I think it's right in the output path. Yeah, because the output's right here, and then these traces just come over here. Anyway, this relay basically cuts off the output when the power drops, so that you don't get that low voltage oscillation once all the main supply rail is collapsing once this main filter capacitor discharges. So we want to make sure that when we hook this up to DC power, that we're still going to get power through this diode in powering up this circuit. And because this is just a half-wave rectifier making the power here versus the full wave over here, which is powering the rest of the circuit, and we can hook it up either way because it'll conduct properly both ways. So we'll want to pay attention to that when we're hooking this up, but everything else, you know, there are no other components hooked up to these lines, so that's all we have to care about. And man, they almost bridged the pads there together. Oh, and the other thing I was going to do is I'm going to replace this main filter capacitor, because why not? They're cheap. So I'm actually going to do that first. So I'm going to go do that. You've probably seen soldering 100,000 times, so I'll come back when that's done. You know, I just noticed they printed on the board 4,700 microfarads. They put in a 22. So I just hooked this back up to the transformer temporarily for a second to demonstrate that, you know, not everything in life is solved by replacing a capacitor. So even though we've gone up in capacity by 50% or so here, you know, this was like a 22 and we go to a 33. You can see that if we probe the same point on the board here, you know, that might be slightly lower amplitude, but we're still getting that sawtooth on the scope. So we still need to put a regulated power supply in here if we're going to expect the audio out to be clear in any way whatsoever and not have a low buzz through the speakers constantly. So let's go ahead and do that. Alright, I successfully removed the power supply here. Let's see that we have the main panel switched hooked up to nothing, and we have the main cord coming in, which is hooked up to nothing on this side, and the front panel switch on this side, so that's going to go to our AC in. We have this connector, which I'm going to salvage off of the transformer to plug back into the board. I might need to make those leads a bit longer, but that's fine. I can, you know, use some of these or something. And then yeah, this board is going to mount in right like this, and I have the, where did I stick that? Fuse holder, right? Fuse holder I'm going to relocate, because right here we can see that if this fuse holder was in here, it'd be hitting some components, and we don't want that. So I'm going to relocate this down where the voltage switch was. I'm going to drill out a bigger hole here and just pop that right in. So that should be fine. And then, I don't know, I'll put something over these other holes. Or maybe I'll just leave them open and not care, because you can't really stick your finger in there. I mean, I guess you can sort of stick your pinky in, but that's a low voltage side, so who cares? Anyway, I need to drill a hole from some standoffs so I can actually mount this in here. I got a standoff kit that I'll probably be stacking a few of these up to make the correct distance. So I'm going to hit the shop and do that. And it's just drilling holes, so you don't need to see that. Alright, we have done some modifications here. So I have moved our fuse holder down to here, because obviously it's not going to fit in there. So fits in there nicely. Even got the little tabs on there for the ears on the back of this thing, so that you can screw it in and it's not going to twist on you. See, that's nice and secure. Not really anything you can poke your fingers in and touch there, so that's nice. Down the bottom here you can see you have 3 new screws for the standoffs that this is sitting on. So you have a nice stack up here of them, and we are just like a beautiful distance from the top. I love how that worked out. And on the inside here, I did have to remove just a little bit of this connector right here. You can probably see on this side it has a fairly long screw hole that sticks out the back, and on this one it was going to interfere with this standoff. This standoff I can't put in because the board is going to be under there, so when this board lays in here, it basically overlaps that part. And luckily it's, you know, down far enough that we're not going to interfere with a headphone jack. But you can see that a little better. Sorry, it's going to be down far enough that it's not going to interfere with the headphone jack. But obviously, I can't put a standoff through the headphone jack, so that's going to like line up there, and it'll be right through the middle of the board. So No standoff on that corner, but we do have the two grounding corners grounded to the case. Those are obviously isolated from the mains and everything, so we're not electrifying this, but yeah, I like where this is. I'm going to have to remove these connectors because I don't have this size of JST. I'm going to flip it over later and show you. But it's not a big deal. I'm just going to solder this in directly. I'm going to use the I'm going to use this connector off of the power supply to go to the board. We'll have to extend that a little bit, and then yeah, wherever the power comes from the switch and from the neutral, I will solder onto there. So that is where I am so far. I'm going to do a little bit of desoldering and resoldering of these connectors, and I'm going to shoehorn everything back in here and power it up, and I will have an amplifier with no buzz. I hope. Alright, so I have done some desoldering and resoldering here. I did manage to get the AC input jack off. If I can find it here. I stuck it somewhere. There it is. So I got the AC input connector off and wired the AC line directly from the switch and the fuse into here. So that's all done and good. I could not for the life of me get the low voltage connector off. It is a 4-pin JST, and I tried with my soldering iron, I tried with my heat gun, switch that off, tried with my heat gun, and it just would not melt all the way through to the point where I could actually move the pins. So I gave up and just soldered this to the top, and quite frankly I think it's probably just as good. I should probably actually put another piece of Kapton over there just to keep that away from the underside of the case. Not that there's really that much risk, but anyways, I did cover the back side, the hot side here with Kapton, just in case of incidental contact. You don't kill yourself. You should still definitely not touch this, but you know, it should be slightly less than lethal if you do ignore that cautionary warning. Anyway, I have the connector wired up with the right polarity here, so even though, remember, it's AC, we have to hook this up in with a positive on this side here, so that when we so that this circuit here with a half-wave rectification can actually work. So I'm going to put this all back together because I have absolute faith in Meanwell to ship me a working power supply, and I have absolute faith in myself for putting this together. So let's just YOLO it, and I'll see you back here when it's put together. Alright, all the boards are back in, and now we get to plug it in. So I figured we'd do this on camera, just in case we go all, you know, magic smoke on this thing. So, nothing should happen because the power's switched off. Just lean over you here. Okay. Now, fire to click. That's good. So, I'm going to hook up a test signal here. Also going to put some actual nuts on here. And I will meet you back in a second. Oh yeah, I clicked off too. Oh, that's perfect. Once I put some knobs on here so that this isn't flopping around loose. Alright, so the proof of pudding is in the scope trace. So I'm going to hook up to ground here. And then I'm going to probe on the positive supply. And when you look at that, it is dead flat. We are still in the same 200 millivolts per division there. You know, the FFT is showing nothing, so we are looking good. I'm going to hook up a signal now and check the output. Alright, so we are hooked up to the output now, and as we can see we have nothing on the trace, which is good because the volume is already all the way down. There is absolutely no sign of a 120 Hz buzz on here, and if we turn this up, we can see that we are in fact working. And I'm going to turn this way down to the 10 volts per division again. So we'll turn this all the way up and see where we start to die. And you know, that's not bad. You know, we are clipping a little bit on the bottom, and you can see we've got a little bit of extra noise in there, but We're not seeing that ripple on the top or anything. This resistor is heating up, so I'll turn that back down. I'm going to call this a success. Now, I'm sure I'm going to get like 10 comments that say, hey, let's actually hear the output of this and see what it sounds like. I'll let you post in the comments why you realize that's a silly idea. So, a little homework for you. Hope you enjoyed this video. I'm going to put this back together and install it back in my on my desk with my bookshelf speakers. And I will see you on the next one.